Okay, good morning, everybody. Let's get started. Checking in with the assignments. Undergraduates, you're moving on to assignment 6. So between now 6, 7, 8, and 9, you're going to be working your way through a series of increasingly strong search methods. You'll be carrying on with that. And then assignment 10, you'll be finishing off other aspects of evolutionary robotics and ready to tackle the final project. Graduate students, hopefully now you are ready to tackle the final project. So for the benefit of the graduate students, I'm going to talk very briefly about the final project. And then for the undergraduates, we'll come back and talk about the final project in a few weeks' time. So graduate students, you have now finished all of the 10 assignments. And as you probably figured out from now, by now you have sort of a base of support to build an evolutionary robotics experiment of your own. For the graduate students, what I'm looking for you to do is to come up with a hypothesis, something you want to test, and propose that idea to us over the next week or so. You can either meet with me during my office hour, which is immediately after class today, or schedule a time to meet with me this week, or come and see me during my office hour on Monday to hash out an idea. Once we have talked and you've hashed out an idea, you are then going to submit next Monday night the first of 8 weekly reports. This first weekly report is pretty straightforward. I propose to do ... And in the following 7 weeks, here are the building blocks to build up towards that final project. So graduate students, you're going to be submitting over the next 8 weeks, 8 weekly reports. Undergraduates, you will finish obviously a little bit later, and there will be time for you to submit 3 weekly reports that describe how you're going to build up to your final project. Make sense? Pretty straightforward? Okay. So graduate students, you will see, I haven't set it up yet, I'll set it up today. If you go into Blackboard, into final project, there will be a weekly report number 1. So next Monday night, you'll be submitting just a little bit of text for that weekly report number 1, which is what you propose to do and how you propose to break it down into 7 bite-sized chunks. Okay. I think I've already mentioned this. There is no final exam in this class. We will all be presenting our final projects orally during the final exam period. So grad students, you're now working on your final project from now until the exam period. Okay, I put some links up here to projects from past years just to give you an idea of sort of the level of complexity we're looking for in terms of projects. Some other places to go look for good ideas is the robotics subreddit. And then just to give you an idea about what we're looking for, here's an example of the first deliverable. This hypothetical student wishes to create a WEGed robot. A WEGed robot has legs and wheels at the end of those legs. And they're proposing 2 hypotheses. The first one is, can a WEGed robot outcompete a robot that has just wheels or just legs? And how general is that approach? We're going to start today talking about legged locomotion. You all get around with legged locomotion. It has its pros and cons. Could a machine that combines the best of both worlds of wheels and legs do better than either alone? That's the hypothesis here. And what about the number of WEGs? Does that matter as well? So they're proposing 2 hypotheses. In this first weekly report, they just have then 8 sentences summarizing how they're going to build up to testing this hypothesis. They're first going to change the standard quadruped that you have at the end of the 10 assignments into a WEGed robot, so put 4 wheels at the end of the 4 legs. Then demonstrate the following week in a video the robot operating as either a wheeled, legged, or WEGed robot, which you could do by freezing the wheels, so the robot has to get around on its legs, or freeze the shoulder joints and allow the wheels to spin, and now you have a wheeled robot, or unfreeze both the shoulders and the wheels and allow it to walk and roll at the same time. Okay, just a demonstration in the second week of that happening. And then in the third week, showing these three robot variants evolving to move over flat terrain. Following week, showing them moving over rugged terrain. And then demonstrating in the fifth week here, a terrain in which the wegged robot outperforms both the legged robot and the wheeled robot. So you can see the student thinking about how to gradually build up to testing this hypothesis for where and when does a wegged robot do better than either alone. Okay, change the four-legged wegged robot into a six-legged one. In the seventh week, show that a new constant has been added to the code where when you set the integer value of that constant, it dictates the number of legs. This is something that a lot of you might tackle in your final project, which is parameterizing your code. At the moment in your code, you probably have 4 lines of code that add the four upper legs, and then another 4 lines of code that add the 4 lower legs to your quadruped. You could imagine putting all of those lines of code, reducing them to just 1 line of code and putting them inside a for loop. And the constant dictates how many times you iterate through that for loop. The more times through the for loop, the more legs you add to your robot. You can parameterize the construction of your robot like that. Okay, and then finally, in the 8th and final week, this hypothetical student proposes to provide proof that a quadruped, hexapedal, or octopedal robot a wegged robot does better than either of the two. So for the graduate students, I'm looking for some statistical evidence supporting your claim that one robot does better than another. Make sense? Okay, again, that's just a hypothetical example that we're looking for. So we also assume that in this first week, when you propose these 8 or these 7 deliverables, they're not set in stone. You may find as you start to work your way through your final project, some aspects of that final project turn out to be more difficult than others. That's fine, just let us know. When you submit a weekly report, in your short paragraph, you might say, previously I proposed that in this week I would show you X, but I've now learned that X is more difficult and I've altered it to Y, and now I'm showing you a video demonstrating Y. It's okay if you change your milestones along the way, but just let us know what the old one was and why you're changing it to the new one. That's fine. Part of what you're being assessed on in these weekly reports is you make it very clear to us that you have a clear path towards your final target goal, which in this case is showing that the wegged robot can, under certain circumstances, do better than a legged or wheeled robot alone. In this case, the student is proposing to change the robot, but again, if you go back and look at projects from previous years, some students have chose to focus on the evolutionary algorithm and tried to improve the evolutionary algorithm while leaving the quadruped robot as is. Others have tackled different tasks or different environments, or 2 or 3 of those elements together. It's up to you. Okay. I think we will leave things there and we'll talk about the written report and the oral presentation, which you're submitting during the exam period. We'll talk about that later. Don't have to cross that bridge yet. Any questions about the final project? No? Okay. Yes?
Do we know that the final presentation is on the 7th of that week, the Tuesday of final?
I checked last night. I think our exam period is Tuesday, May 7th. I forget the time. I think it's mid-morning. We'll fill it in when we get a little bit closer. Long way away, right? Okay. All right, so we are making our way through the history of evolutionary robotics, which is not a very long history. We're approaching the end. We're going to finish up this pair of lectures on minimal cognition, and we started into lecture 10 last time, which we'll finish today, where we were looking at this not so minimal anthropomorphic robot arm, anthropomorphic meaning human-like. And then we will start into lecture 11 today, the first of our 2 lectures on locomotion. Why getting from point A to point B is intimately connected with intelligence. So back to lecture 10, an active categorical perception. I introduced this idea of ACP to you last time by challenging you to imagine rolling your palm along the top of an object. I think I might have confused the issue here of active categorical perception. The main message here is that when we, or a machine, interacts with its world, the continuous flow of perception often congeals into discrete categories. This object rolls when I move my palm along the top of it, or this set of objects roll when I move my palm along the top of them. But this other set of objects, when I perform the same action, those objects slide. So suddenly, these categories emerge out of the interactions from the world. They're not dictated by a teacher or some other element. I introduced this further idea of ACP, which is when we start to interact with the world and these categories start to become apparent to us, there are additional actions you can perform that reduce the sensory differences within objects that belong to the same category. And you can also perform actions that magnify or exaggerate the differences between perceptual cues coming from these two classes. And I'm going to show you with this robot exactly what it means. I'll show you an example of reducing these within category differences at the same time that you're magnifying inter-category differences. Okay, so just a reminder, we're dealing with this robot here. It's got 7 rotational joints in the arm and 10 motors in the hand, 10 joints in the hand. All the 10 joints are being controlled by two motors, one which is pulling the motors open and another one that is pulling the motors closed, which we saw last time when we started to look at the CTR and N for this robot. We have all the 7 arm proprioceptive sensors down here. So the robot knows the angles of all the joints in its arm. It knows all the values of the 10 touch sensors in the hand, 2 in each of the 4 fingers, a 9th in the thumb, and a 10th touch sensor in the palm. And also the hand proprioceptive sensor, so the angles of the 5 fingers as the arm is moving. That's our sensor layer. We see here that we have a hidden layer, and then finally we have our actuators here. So we have 14 motors that are controlling the 7 joints, which seems a little bit odd. We have 2 motor neurons attached to each of the 7 hinge joints. Why the overkill? Why not just 7 motors?
Is it more like how the human arm works? Like we have 2 muscles that control one joint?
We have 2 groups of muscles for most of our major joints, for example, bicep and tricep. And these are known as agonist and antagonistic. Agonist and antagonist muscle groupings. Muscles cannot push, all they can do is pull, right? So if I want to flex my arm in towards me, my bicep flexes. If I want to extend my arm again, my bicep relaxes and my tricep flexes. So they built in this additional detail where you can imagine each pair of motor neurons here pulling on their respective joint. Just an additional anthropomorphic detail they put in. 2 more hand actuators, 1 muscle group, if you like, which is flexing the hand, and the second motor neuron, whatever its signal is trying to open the hand. And these 2 are fighting against one another, agonist and antagonistic, to open the hand. So far, so good? Okay. The unique thing about this robot, the reason why we're spending today talking about it, is neuron number 47 and 48. These are going to represent the robot's guess about which object the robot is interacting with. Is it interacting with the sphere or the ellipsoid? What you might imagine, if you've seen neural networks before, is that if we place an object in front of the robot, which causes all the sensor neurons to start firing, signals flow from the sensor neuron to the the hidden layer, and then up to the motor layer and the categorization neurons. You might imagine that, for example, if the value of neuron 47 is greater than the value of 48, that's the robot saying, I think I'm in the presence of the sphere. If, on the other hand, Neuron 48 has a larger value than 47. That's the robot saying, I think I'm in the presence of the ellipsoid. Kind of makes sense. So it would be the easiest thing you could imagine to enable the robot to tell us which of the two objects it thinks it's interacting with. That is not what the researchers did here. They used something much more complicated. Why did they not use this simpler approach? Why not just train the robot to light up neuron 47 when it's in the presence of the sphere, and train it to light up neuron 48 when it's in the presence of the ellipsoid?
Maybe it would potentially be in the presence of a different shape and it wouldn't fit into those categories.
Possibly. So we put a cube in front of it. Then what does it do? All right, now we're going to train it to recognize cubes as well. So we add neuron 49. Now we introduce rectangular solids, and we introduce neuron 50. We introduce soft objects, and we introduce neuron 51. What's the problem here?
The robot isn't discovering the categories if we're providing a neuron for every category.
Exactly. Remember that what we're trying to do here is not tell the robot, well, there are these two different categories, but we don't want to try and cheat by saying you've got one neuron for this category type and another neuron for this category type. We want it to some degree to try and discover these categories on its own. We're going to see how they evolved the robot to do that in a moment. There's another problem with associating one neuron with each object type. What is it?
You could have infinite neurons for infinite object types.
How many object types can you recognize, right? It's probably more than 2. Again, we don't quite know how to enumerate it, but it doesn't seem like a good use of neural real estate to keep assigning one neuron to every specific experience you or the robot might have. It doesn't seem scalable. This is a controversy that's been raging in neuroscience basically since the beginning, and the meme used to describe this controversy is the grandmother cell. So you have one neuron somewhere in your brain that only lights up when you see your grandmother, think about your grandmother, and so on, which may be the case, but again, there are lots of unique perceptual categories out there, and it may not, you do have a lot of neurons, but it seems wasteful to assign one to just one element, right? Presumably most of the time you're not thinking about your grandmother, so most of the time that grandmother cell is not being used. Doesn't seem like a compact way of doing things. So perhaps the brain distributes the recognition of categories across multiple neurons. This latter hypothesis is harder for us to wrap our mind around. Again, thinking about thinking could be misleading. It's easier for us to think about categories and associating them with one neuron or one small neural circuit, but doesn't seem very scalable. So can we try and work against our intuitions and provide an alternate mechanism for our machines to learn categories in the world without having to assign one neuron for every category? All right, I'm building this up quite a bit. Before we reveal how the robot does this, let's have a look at the equations down here. This is a good way to refresh our intuition about CTRNNs. This robot has a total of 48 neurons. It's a CTRNN, so how many ordinary differential equations do we have to describe our CTRNN? 48. We've got 48 ODEs, right? One for each neuron. And you'll notice that we have two sets of these ODEs. The first one, with the first 22 ODEs, have this mathematical form. And ODE 23 through 48 inclusive have this form. Why? Why did they break up the description of these neurons into these two different groups? What are neurons 1 through 22?
Oh, I guess I was going to say the opposite is 23 through 48. Are those the hidden neurons?
Those are the hidden neurons, 23 through 30. So it includes the hidden neurons.
So the first 22 are sensor neurons.
That's right. The first 22 are sensor neurons, and they're described by this ODE. And the following neurons are the hidden neurons and the motor neurons and the categorization neurons, everything other than the input neurons. Tell me about the equation describing the sensor neurons. How did the sensor neurons behave?
Well, it looks like it neglects the term, or like the term with all the omega and sigma, probably because the input is so much greater than the values of the summation that they can disregard it.
Exactly. So they've thrown out the summation altogether, and they said, listen, the sensor neurons, they just receive a value from their associated sensor, which could be the proprioceptive sensor in the arm, or a touch sensor in the hand. So the value of the sensor neuron is basically going to be I sub I, the value of the sensor itself, multiplied by G, and I think there should be a G sub I there. I think they made a mistake, which is the gain associated with that, the ith sensor neuron, divided by tau. Remember that tau is the time constant. So this means the value of the sensor neuron is almost the same as the value of the sensor that it's attached to. But the rate of change of the sensor neuron can be sped up or slowed down by evolution by setting the tau sub I. Right? And if the sensor itself does not fire, the sensor neuron will gradually decay back towards 0. Okay, and then the equation for our hidden neurons, motor neurons, and categorization neurons is pretty much what we've seen before, right? Okay. Okay, let's now have a look at neuron 47 and 48. Let me walk you through the intuition for what they've done here, and then we'll talk about the math itself. Again, they don't want to try and assign one neuron to each category. So neurons 47 and 48 together are going to signal whether they, the two neurons, think that the robot is in the presence of the sphere or the ellipsoid. And the way they're going to signal that is we're going to look at the values of 47 and 48 during the last 5% of the robot's experience with a given object. So you'll notice if we look over here for a moment, there's the term sum y47t plus beta 47. So y47 bracket t, we're going to introduce this notation, which means the value of the raw value of the 47th neuron at time step t. That's the raw value. And then you'll remember that we push it through sigma here, which squashes the value back to some value, in this case between 0 and 1. Doesn't really matter. We're going to look at time steps that range between 0.95 uppercase t and uppercase t. So uppercase t is going to represent the total number of time steps that we evaluated the robot in when it was put in the presence of just one object. So in your code at the moment, you're running your simulation for 100 time steps or 1,000 time steps. That number, 100 or 1,000, that's uppercase T. So we're going to look at the values of neurons 47 and 48 during just the last 5% of the time step. So the robot can sort of do what it wants with the object. It can roll its palm along the top of the object. It can grab the object, pick it up and shake it. It can do whatever it wants. And then just at the end, we're going to look at 47 and 48, and we're going to read off from that whether the robot thinks it's in the presence of a sphere or an ellipsoid. Make sense? Okay, let's introduce a new visualization for a moment. This is going to help us visualize what's going on. What we're going to draw here is what's known as a phase diagram. And a phase diagram is a nice way to represent how values are changing over time. We are not going to place time on the horizontal axis. Instead, we're going to place the value of the 47th neuron And this is going to actually be the entire sum here. I'm just being lazy. But on the horizontal axis here, we're going to plot the value of the 47th neuron. And on the vertical axis here, we're going to plot the value of the 48th neuron. Let's assume at 0.95 uppercase T, the value of the 47th neuron is this, and the value of, the value of the 47th neuron is the x coordinate here, and the value of the 48th neuron is the y coordinate here. So this, the coordinate value here is the value of 47 and 48 at 0.95 uppercase T. Okay, that's what it is at 0.95 T. At the next time step, the value of neuron 47 and 48 are going to change a little bit to something. And we'll place a dot at that pair of values. If we then connect these dots with a line, we're starting to draw a trajectory that's going to move through this two-dimensional plane. So whatever the value of 47 and 48 is at the next time step, we go there, next time step, next time step, next time step. And we keep going until finally we reach a point at time uppercase T. And the start of this trajectory, just to remind ourselves, is at 0.95 uppercase T. So if we think about the values of 47 and 48 changing over time, they're drawing a trajectory in phase space, which gives us this phase diagram. So far, so good? Okay. We are then going to place a rectangle around this trajectory. We're going to place a bounding box around this trajectory. And how do we create this bounding box? Well, we're going to look for the minimum x value, which in my little cartoon happens to be here. We're also going to look for the maximum x value of this trajectory, which happens to be over here. We're going to look for the minimum y value, which is here, and the maximum y value, which is here. So we've taken min x, min y, and max y, which gives us a bounding box around this trajectory. If the robot traced this trajectory when it was in the presence of a sphere, we're going to call that R sub SE. So the S reminds us that it was a sphere that was placed in front of the robot during the ETH evaluation, or the ETH trial, I think they call it here. Remember that we're going to expose each CTRN to 16 trials. We're going to place these 8 objects in front of the robot when it's either in this position, and then those 8 objects again when the robot's arm is in this position. So there are 16 bounding boxes that we're actually going to create here. So this, imagine that in the first of the 16 trials, we placed a sphere in front of the robot, and value 47 and 48 did the following. We now remove the sphere, we put the robot's arm back to the initial position, reset the CTRN, and now we place an ellipsoid in front of the robot and turn on the same CTRN again. The robot may or may not do something different in the presence of this new object, right? Remember, the robot doesn't know what the object is. It just feels the object and does what it does, and values 47 and 48 change again. Let's assume in this case that it traces a line out here. This is what we get in the second of the 16 trials. And again, we place a bounding box around this trajectory by finding the min x, the max x, the min y, and the max y. We're going to refer to this as R sub d for ellipsoid during the ETH trial, which in this case is the second of 16 trials. So far, so good? Okay. Remember, we have 16 trials here, so we're going to trace a total of 16 trajectories, which is going to give us 16 bounding boxes. It's going to give us 8 R sub S's, and it's going to give us 8 R sub D's. So I'm going to erase this now, and we're going to draw some of the 16. I don't have different colored chalk here, so we'll just do the best we can here. Here's one of the R sub S's, another one of the R sub S's, another one of the R sub S's. Here's one of the R sub D's, another one of the R sub D's, and a third R sub D. Each of these has a bounding box around it. Close enough. We are then going to place two more bounding boxes. We are going to place C sub S for the category S, and this bigger bounding box, we're going to place it so that it bounds all the R sub S's. We're then going to take all the R sub D's, all 8 R sub D's, and we're going to place C sub D around those. So we now have two big bounding boxes, one for the spheres and one for the ellipsoids. We want our robot to categorize or distinguish between spheres and ellipsoids. So we've now described all aspects of this experiment except the fitness function. The fitness function is going to be a function that operates on these bounding boxes. And this fitness function should have higher values when the robot distinguishes between spheres and ellipsoids. And the fitness function should have lower values when the robot is having a harder time distinguishing between spheres and ellipsoids. How do you think the fitness function is going to incorporate these bounding boxes?
Just look for the overlap between the larger blocks.
Look for the overlap between the boxes. The more overlap between these boxes, the more similar, on average, the trajectories are between 47 and 48 for these two different objects. The less overlap there is, the better the robot understands the difference between these two objects. By moving these bounding boxes further and further apart, the robot is magnifying between category differences. Okay, so let's have a look at this fitness function. It's actually a sum of two fitness terms, F1 and F2. Let's look at F1 first. We notice there's a summation term in here, so we're going to sum over all 16 evaluations. So uppercase E here represents 16. And we're going to take 1 minus d sub E over d sub max. We already know when we see this 1 minus or this negative sign that this ratio here is a penalty term. We want to try and get this ratio to be as small as possible. D sub E, as it says down here, is the Euclidean distance between the palm of the robot's hand and the object. The closer the palm is to the object, the smaller d sub E is. And d sub max is the maximum distance that the robot can move its palm away from the object. So what is F sub 1? What is F1 rewarding for?
How far away the, well, not how far away, but how close the sphere is to the robot's hand.
How close the robot's palm is to the object, right? You can imagine that the 99% of the things that the robot might do involve waving its hand around and never actually touching the object, which is going to make things very, very difficult on evolution, right? Obviously, if you don't touch these objects, the robot is going to have a very hard time distinguishing between them. Our robot has no camera, there's no visual sensors here. It's got to do everything by blind touch. So F1 is giving the robot a pretty strong hint. Contact the object. Manipulate and play with the object. Okay, so if the robot manages to keep its hand in contact with the object, d sub E is 0. And 1 minus 0 is 1, so the max value for F1 is 1. If it never touches the object in all 16 trials, and for example moves its arm as far away from the object as it can, it gets an F1 of 0. So F1 ranges between 0 and 1. higher values being better. If it manages to get a value of, if it does get an F1 value below 1, then it's not always keeping its hand in contact with the object, and it's not going to be able to benefit from the additional points of F sub 2. So F sub 2 is just set to 0 if F sub 1 is less than 1. As evolution proceeds and a CTRNN manages to get a value of F1 equals 1, it unlocks the additional points it can collect from F sub 2. This mechanism, now written mathematically, we've seen before. What is this mechanism? This composite fitness function is basically telling evolution, focus on F1. Once you figure F1 out, then you can tackle F2.
I want to say scaffolding.
So it's exactly scaffolding, right? Walk before you can run. So mathematically, we're building in a scaffold here, which is saying, listen, we're not going to tell you how to categorize between objects, but we'll give you a hint. Stay in contact with the object. How you manipulate that object to magnify intercategory differences, that's up to you, right? Okay, so assuming that it does, and I apologize if you can't see from the back here, the CTRNN is able to collect additional points from F sub 2, which is, again, 1 minus a ratio. And you'll notice, again, we've got a negative ratio, so we're trying to penalize this ratio. The smaller the ratio, the better. The numerator, as Scott mentioned, is the amount of intersection between C sub S and C sub D, the two big bounding boxes. That's the intersection. The smaller that intersection, the better. This is a penalty term, right? We want this to be as small as possible, so no overlap is optimal. If the overlap is 0, 1 minus 0 is 1, and you get maximum points for F sub 2. You'll notice the denominator here is the minimum of the area of C sub S or C sub D, whichever is the smallest. Why are we dividing by the smallest? That's the maximum amount of intersection, right? So usually when we see these ratios, like in F1, it's a normalization term. So by throwing that in there, we guarantee that F2 ranges between 0 and 1. F sub 2 means the robot has no idea about spheres and ellipsoids. F2 equals 1 means the robot knows the difference between spheres and ellipsoids. Okay, so there's a lot of buildup and much more complex than you would imagine if you had one neuron for one category. Let's hope that this complexity was worth it. Before we see that, I'm going to play you two videos. These are, again, it's the same CTRNN. This is the best evolved CTRNN that they were able to obtain. In the top video, as you can see, we're going to show you a bunch of trials with the robot's initial pose at pose A, and in the second video, it's the robot's arm in pose B. So two videos, but it's the same CTRNN. If you watch carefully, and again, I apologize for the quality of the video here, you'll notice sphere is written in red and ellipsoid is written in green, and between them is a blue arrow pointing up. What does the blue arrow pointing up mean?
It's the how much of the robot's guess is going towards which direction.
It has something to do with the robot's guess about ellipsoid and sphere. The arrow is pointing straight up. What does that probably mean?
This side up.
This side up, maybe.
It hasn't decided yet.
It hasn't decided yet. It's shrugging its shoulders. I don't know, right? It's hard to see from the video here. I think in this first clip we're going to see it's actually in the presence of an ellipsoid. You're going to see as the video runs that the blue arrow doesn't continuously rotate towards the sphere or the ellipsoid. It's going to flip from either vertical to point directly at the sphere or point directly at the ellipsoid. Back, back, back. Why is it going to move in these discrete jumps? What do these three conditions mean? What is the blue arrow representing?
I guess which value of those neurons is higher, maybe?
Not which value of the two neurons is greater.
Which one is the robot thinks at that point the object is either?
It's its guess, right? Obviously, if it's pointing at the sphere, it's guessing that it's the sphere. But why these three discrete categories?
Does it link back to the phase diagram?
Absolutely, it does. How so?
So would each side be one of the individual category squares, or the middle would be overlap?
Exactly. So if at a certain point in time, the value of 47 and 48 is this value, what category does the robot think it's in the presence of?
Is it undecided?
It's undecided, right? This point is neither inside the C sub S, which corresponds to spheres, and it's also not inside C sub D, the category representing ellipsoids. So arrow points straight up. If, as it starts to move, the value of 47 and 48 drifts inside of C sub S, the arrow is going to switch and point to sphere. As it keeps going, if the value of 47 and 48 drift inside of C sub D, the arrow is going to point towards the ellipsoid. If there is overlap between the bounding boxes and the value of 47 and 48 drifts into that intersection region, where does the arrow point? Straight up again, right? If it's in neither of the bounding boxes or inside of both bounding boxes, the robot says, I don't know. Okay, let's have a look. Actually, maybe it's easier to play it here so you can watch the arrow. Hold on, let me restart this.
Could you zoom in on the slide a little bit?
That's a good idea. Maybe I can. How did the robot do?
Badly.
Badly? You'll notice the ellipsoid is, the major and minor axis of the ellipsoid are almost equal. So it's almost a sphere. Unless you're watching carefully, it's actually hard to see whether you're looking at a sphere or an ellipsoid. If you look closely,
So does the color of the text change depending on what it is? Like, are we changing between the sphere and the ellipsoid? So keep changing.
oh, good point. You know what? I never noticed that before. You're right. Green is what the actual object is. Good catch. I don't know how many times I presented this video. Thank you. That helps. How's the robot doing? Pretty good, right? Not bad. Okay. So that's with initial pose A. Let's have a look at initial pose B. Same C tier and N. That's all 16. How did it do? A plus, right? Okay. How does the robot distinguish between? We know the mechanisms about how. We know how it was trained to solve it. What solution did the robot come up with?
It's rolling them to see how far they're rolling.
It's definitely rolling them, that we can see. It's rolling them to determine.
The distance it rolls back compared to its circumference.
Maybe there's a little bit of rollback in some cases.
I was wondering if it like has a definitive path that spheres always go, and ellipses still always think that.
Maybe we could watch the video again and watch all the spheres. Is there a particular trajectory that it traces for the spheres?
Looks like it uses two orthogonal, and then it rolls back, and then it rolls to the side, so it's kind of fishing for that. If it happened to be a line, an egg on the side, and you rolled it, you wouldn't know that it wasn't.
Exactly. So if I put a sphere and ellipsoid in front of you and you only rolled it along one axis, if you chose poorly, it would be hard. You would not be magnifying the inter-category differences, right? They'd all be mixed up together. So maybe it's rolling it along one dimension, a little bit along another to sort of feel things out, maybe.
This might be a clue, but like whenever it was a sphere, it seemed to like choose the ellipsoid at first, but then like switch it.
You notice sometimes, right, it says, I think it's the ellipsoid. No, wait a second, it's the sphere. So it's not perfect at every point in time, right? So maybe not A++. Takes it a little while to figure out, but again, remember, we're only asking it to give us the right answer in the last 5% of the time of each of these individual clips.
But like maybe it's categorizing spheres as like a subclass as ellipsoid, so it's like an ellipsoid until this happens.
Maybe that's an interesting idea. Maybe. Again, I've presented this video and watched this video hundreds of times. I still don't know. Thinking about thinking is misleading. In the robot's mind, there is a clear difference between spheres and ellipsoids, but if you watch the actual action of the robot, it's very subtle, right? It doesn't grab spheres and put them over here and grab ellipsoids and put them over here, which in theory it could do, right? So it's often not that obvious. I mentioned last time lesion studies. We could go in and start to knock out some of the neurons in the CTRN and see how its behavior changes. And now maybe it always thinks everything is a sphere or everything is an ellipsoid. You could start to dig down into this one evolved CTRN to try and get a better answer. But as usual in evolutionary robotics, the answer is not obvious on the surface. Okay, so that's the robot's behavior. Here's evolution. So they did 3 evolutionary trials. They evolved the robot 3 times. And in all 3 cases, within 250 generations, there was one CTRN in the population that was getting a fitness value of 2. So it was getting as good as you could get for F1, which is 1, and getting as good a value as you can for F2, which is also 1. Perfect. So it's not that difficult to task. It takes quite a while. You can see in trial number, whatever this is, 2 or 3, it took a little bit longer, but it eventually got there. So it's not that difficult a task to solve. Let's now look inside the mind of the robot. We're again looking now at this phase diagram. We've thrown out the individual trajectories traced by neurons 47 and 48, and we're only leaving the bounding boxes. Like we saw in the minimal cognition experiments, we're taking the best CTRNN that we were able to obtain, and we're playing it back now, not 16 times, but several hundred times. We're going to place the sphere in front of the robot several hundred times. And we are then also going to, we're going to place the ellipsoid actually 180 times in front of the robot at different horizontal orientations underneath the robot's palm. Yeah? So it's the same object, it's the same ellipsoid, it's just rotated differently 180 times. As you can probably guess, the small ellipsoids here are the R sub S's and the R sub D's. And the one big bounding box here, the dashed line, this is C sub S, the category box around spheres. And the bigger dashed box is C sub D, the category box placed around all the ellipsoids. The color, or the gray or black of the box, represents the actual object that was placed in front of the robot at that time. Question?
Why is the one for the ellipsoids not up more? Because there's 2 black boxes that are kind of in
Ah, right. So I'm sorry. So the two dash boxes, those are what came out of evolution, right? We trained the robot on the 16 cases, and that's what the dash boxes are. And then we exposed it to these novel conditions, which are all the small boxes. Good catch, right? So tell me about this. So here are 2 out of the 180 ellipsoid presentations. What does the robot think about these 2 ellipsoids? Think there's spheres. This one, it says, I don't know, but it looks more sphere-ish than ellipsoid-ish. And this one, it says, yep, that's a sphere, for sure. Okay, so I made a couple mistakes out of 360 questions, 180 ellipsoids and 180 rotations of the sphere. There's no rotation of the sphere because it's radially symmetric. You'll notice in the case of the sphere, it's a little more clear there are 2 groupings of these bounding boxes. Where are these 2 groupings coming from? They still all fall within the category box of spheres, so it knows they're spheres, but they're kind of almost like 2 subcategories of spheres.
Does it have to do with the initial position of the arm?
Exactly, right? Initial position A and B. So 90 of the spheres were presented to the robot when it was in pose A, and the other 90 when it was in pose B. So it says, okay, those are both spheres, but they feel slightly differently, which is not surprising, right? This is what it feels like to interact with the sphere, and this is what it feels like to interact with the sphere. Not so clear in the case of the ellipsoid. One other detail here is you'll notice that all of the boxes in here, they don't perfectly overlap one another. But in the case of the sphere, we have 90 presentations of the sphere in pose A. That's exactly the same initial conditions 90 times in a row, but we're getting 90 slightly differently placed boxes. Why? Has to do with the detail we haven't mentioned yet, but you might be able to figure it out.
Are they including any uncertainty in the sensor reads?
They're putting a little bit of uncertainty or noise. This is a common technique in robotics, which is to sprinkle slight errors everywhere at the sensor layer, the hidden layer, the motor layer, the physics engine. Because when a robot operates in the real world, there's lots of noise, lots of uncertainty. Heraclitus said, man never enters the same river twice 2,000 years ago, right? Everything's slightly different. In a physics engine, there's not as much heterogeneity, so we can cheat a little bit by sprinkling a little bit of noise. So the robot never does exactly the same thing twice. You'll notice there's lots of other interesting things you can see here as you view the mind of this robot. The ellipsoid category box is larger than the sphere bounding box. There's nothing in the fitness function that says anything about what the size of these boxes should be, nor their position, just that they shouldn't overlap. Why might the ellipsoid box be larger than the sphere box?
Well, taking the example of rolling it, for example, the sphere is going to kind of feel the same no matter which direction you roll it, but an ellipsoid can have multiple different kind of input depending on how you roll it.
Exactly. The size of the bounding box is kind of telling us that from the robot's point of view, it's having a broader set of sensory experiences when it interacts with the ellipsoid than it is with the sphere. It wasn't in the fitness function, it's kind of just a side effect of this evolutionary process. Okay, so that's the best robot that we see here. Here is, let's see, here is from run number 2. So this is from the second evolutionary trial, the best robot, the second best robot, and the third best robot. In the left panel in each of these figures is showing the, it should be showing, yeah, the sphere bounding box and the ellipsoid bounding box, more or less. What's different or similar between these 3 CTRNNs? It's actually showing multiple boxes here. I'm not sure why, but just in your mind's eye, just put one big box around these and another big box around these. These are three separate C-tier-Ns. They're coming from the same evolutionary trial, so they may be related. They may not be related. It's hard to tell.
The best one is only simply separating them on one axis and not both.
So that's right. So in this case, the sphere box is above the ellipsoid box, only separated by y, or by 48, not by 47. It's almost like it's not using 47. Not so in the other cases. What other observations can you take away from these three figures?
The size of the sphere
And the ellipsoid box, yep. What about the relative sizes?
they're different between the trials.
They're different, the sizes themselves, yep.
It looks, I guess, like the one with the most white space is the third best, and like the least white space is the
That's interesting, yeah, true.
The ellipsoids have a bigger space than the spheres.
Exactly, like we were just discussing, right? So for all three of these C-tier-Ns, there's a broader range of experiences when they come into contact with the ellipsoid than the sphere. Yep.
I guess it looks like for the most fit, the sizes of the different categories get closer together. Like in the third best, this ellipsoid one is like much bigger than this sphere one.
Much bigger. They had to zoom in to even see the sphere bounding box.
The ellipsoid makes up a broader range of I don't know, like not categories, but experiences.
Right, so the range of values of 47 and 48 are bigger in the ellipsoid, right? Whatever that means. What about the actual distance, the amount of separation between the two bounding boxes? Are they really far away from each other, really close? What does that tell us?
The further away they are, the like more maximize the distance between them.
If those two big bounding boxes were further from one another, that's the robot further exaggerating intercategory differences, but there isn't that much here. And remember, the ellipsoid feels very similar to the sphere in this case. So those edges between those boundaries are pretty close to one another. Okay. That concludes our discussion of the ACP robot. Let's come back to the benefit of going through all this effort. Let's imagine we continue this experiment, we re-evolve the robot, and now we put it in the presence of cubes. We're going to use the same sphere, same ellipsoid, and introduce a third cube. We'd have to make some changes to the fitness function. What changes would we make to the fitness function? There's three types of objects we're going to introduce. Do we need to introduce a 49th neuron? No. We can pack or embed an understanding of cubes inside the same neural real estate. We can use the same two neurons. What do we want them to do now?
You'd have to modify your fitness function if you have multiple areas now to check overlap for.
Yes, how so? What are we looking for? We're going to have three bounding boxes now, C sub S, C sub D, and C sub C for cubes. What are we going to do with those three bounding boxes? Or what do we want evolution to do with those three bounding boxes?
Make them as far apart as possible.
Maybe. We didn't do that before. Do we want them to be as far away from each other as
The overlap
possible?
as small as possible.
Sorry?
Make the overlap as small.
Make the overlap as small as possible. Look at all the pairwise overlaps between the three bounding boxes and zero them out, right? No overlap. Is that enough? We're trying to teach our robot. Are we being good parents? Is there some additional information that we want the robots to take away from these three kinds of objects?
Minimize the size of the bounding boxes.
Maybe. We could try and do that. If we included a term that minimized the area of the bounding boxes, what are we trying to evolve the robot to do? Trying to get it to minimize the bounding boxes, but what does that mean from the robot's point of view? from its perception of its world.
To minimize the difference within a category?
Exactly. That would be a term that would reduce within category differences. Exactly. We could include that. What else might we want to impart to our robot about the nature of spheres and ellipsoids and cubes?
Oh, that a sphere and an ellipsoid are closer together.
You all remember back to your childhood, which of the three doesn't belong? A very important game that all of us play. It's a game that's played in lots of cultures all over the world for a very good reason. Not only are there categories, but some categories are closer or further away from each other than others. If you think about that, close and far away, that is a very abstract concept that's now taking us beyond ACP into some of the upper echelons of abstract cognition. We obviously don't mean literally far away. It's not that the sphere is here and the cube is here. What is that distance called? For those that have studied AI and machine learning. Distance of what? This is known as semantic distance, right? Something to do with the meaning of these categories, and that some meanings are closer to one another than others. One of the nice things about this bounding box and phase diagram approach to categorization is it gives us a geometric platform on which we can literally represent distance of abstract concepts. So we might include an additional term into our fitness function. We might include an additional term into the fitness function that says minimize intersection and put C sub C, the cube category, further away than C sub S and C sub D are to one another. We're telling the robot, you experience those objects however you like, but one of them does not belong. It's more different than others.
Can you generalize that?
Can we generalize that? How would we generalize that? Now we place hundreds of different kinds of objects in front of the robot. How do we generalize this approach? If we have hundreds of objects and we say for every pair of objects, some are closer and some are further, we might actually assign numbers and say that's the distance, the Euclidean distance that those bounding boxes should be from one another. We could actually enforce that. Could the robot obey? With 3 objects, probably yes, right? Put C sub C further away from C sub S and C sub D, but hundreds of objects?
You could do a self-organizing map, the next layer up, basically take all the bounding boxes and see how similar the bounding boxes are.
Maybe, right? With 2 dimensions, 47 and 48, without doing some fancy math like self-organizing maps, it would be hard for evolution to figure out where to put all the bounding boxes to respect the fact that we want this pair to be this close and this pair to be this far and so on. There's something else we could do that might be simpler than self-organizing maps. Add another neuron. Okay, we're going to concede and add neuron 49. And now we're not dealing with bounding boxes, we're dealing with bounding volumes, right? And it might be easier for the robot to pack in these semantic distances given 3 neurons.
I feel like that's kind of like artificially imposed on the robot though. Like, what if the way that the robot is experiencing squares and ellipsoid and spheres, like what if the way it feels that like a sphere is more similar to a square and not an ellipsoid?
Exactly. We're kind of cheating now, right? We started by saying we're not going to try and impose these categories on the robot. They should emerge on their own. We're now trying to sort of force the issue by adding in additional fitness terms. This is an area of argument in AI and machine learning and robotics in general, which is how much should we tell our machines and how much should we allow them to discover for themselves? Maybe the machines learn that there's no difference between spheres and ellipsoids. They're the same thing. Yes, cubes, they're different, but for us, machines, no difference between this object pair. But for humans, we do see a difference between these objects. So maybe our semantic understanding of the world starts to diverge from that of machines, and that takes us into dangerous territory. Remember my metaphor before about friend or foe, or danger and opportunity? If the robots distinguish between danger and opportunity differently from how humans do, that does not sound like a very safe machine to me. So at the moment, we're not tackling trying to create safe machines. We're just focusing on autonomous machines. But if we want safe machines, they should probably be able to distinguish between objects in like us, but not in the way we do. We might have different bounding boxes. Doesn't matter about our mental representations. As long as when we both meet machines and humans in the real world, we both recognize the difference between children and adults, cubes and ellipsoids, all the other distinctions that matter to us, our machines better understand them as well.
So they only worked with rolling objects. I mean, we've talked a lot about sliding objects. Did they ever do any experiments?
They did not take it any further than what I've told you today. Again, for a final project, this might be something to tackle.
You'd have to do sort of you'd have to see the point rolling across the multiple sensors in the hand, I think, you know. If
To
it
do
was just sliding, you couldn't tell that it was necessarily not a sphere because it had the same value.
Maybe.
Unless you were looking for a change of.
Yeah, could be. So distinguish between rolling and sliding objects. This might be a little bit more difficult. I don't know. It'd be a good experiment to try and see. Okay, I love this experiment. As you can see, it's a great springboard for tackling some of the more difficult aspects of abstract cognition. That's what I want you to take away from this lesson today. Again, we started with minimal cognition, very, very simple Space Invaders robots, doing very, very simple things. But you can start to see how with an evolutionary approach, you could start simple and gradually evolve more and more cognitive machines. All right. So let's go back to the schedule for a moment. We have just a few minutes left, so let's switch gears now. We're going to start in on lecture 11 on legged locomotion. I forgot to mention, while we're now looking at the schedule, I am not going to be here this coming Thursday. You're going to have a guest lecturer, Sam Kriegman. Sam is one of my PhD students, and he's going to tell you about some of his PhD work. And his PhD work is on soft robots, which we're not going to talk about until lecture 27. So he's going to give you a preview of soft robotics. And then when I'm back the following Tuesday, we'll finish off lecture 11. Okay, but let's at least start today. We're going to do this two lecture series on locomotion. As I mentioned several times now, there is an intimate connection between movement and intelligence. And if you ever question that intimate connection, you can revisit the question posed by a neuroscientist quite a while back, which is, why don't plants have brains? They don't have brains like we do. I'm not saying they don't think. Depends on how you define thinking. But there seems to be much less mental life going on in plants than there are in animals. If you plump on the option of deciding I'm going to stay put, I'm going to stay here, and I'm going to just try and grasp whatever nutrients come my way, versus the other strategy, which is I'm going to go to the food. They're very different strategies. The minute you start to move around in your world, things get very scary, because suddenly when you're moving, the world seems to move relative to you, right? The visual scene falling on my retinas at this point in time is very different from what's falling on my retinas now. Luckily, my nervous system is able to reduce the intra-category differences between this perceptual state and this perceptual state. But as we've just seen, it's not a trivial thing to do. So roboticists are interested in smart machines, but they start at a very different point than people that work on deep learning and recognizing objects and images. There, the starting point is pattern recognition. In robotics, the starting point is usually locomotion or movement. So to introduce this topic, I've pasted a few pages from the table of contents of one of my favorite books. This is The Principles of Animal Locomotion. We're going to spend lecture 11 and lecture 12 looking at biomechanics now, the mechanics of biological movement. It's a fascinating subject. It would be a whole course in and of its own right. We're just going to touch on this. For those of you that are interested in biomechanics That's the Bible right there. This book is arranged basically, it's organized in terms of all the different ways that Mother Nature has found to get organisms from point A to point B. And she's done it using just one Lego brick, which is muscle, right? There is one organ or one tissue type that produces all of the motion that we see in nature. Muscle is amazing. You put it together in different ways, and you get, for example, locomotion on land, you get burrowing, you get peristaltic motion. Here's a little cartoon of an earthworm that is gradually pushing its way through some loose soil. As you can see in the cartoon here, peristaltic motion. Peristaltic motion is the idea of increasing and decreasing the volume of different parts of your body along the length of your body. And if those changes in volume propagate backwards along your body, you will generate force that moves you forward. When you swallow a piece of food, your throat is using peristaltic motion to move the food down towards your stomach. Peristaltic motion is actually everywhere in nature, again, controlled by muscle. Muscle allows you to walk, run, hop, jump, climb, crawling and burrowing, we already mentioned, gliding and soaring. It allows you in the air, hovering, powered forward flight, wing beats. Moving on the surface of the water, not so easy for us or other large animals, but if you're small enough, you can literally walk on water. Swimming with oars and hydrofoils, swimming by undulation, and finally jet propulsion. Again, the animal kingdom is amazing. It's amazing in terms of all the different ways that muscle has been adapted to get animals from point A to point B. Okay, this is a lot of the inspiration for mobile robotics. Let's end today just by starting to think about this. Let me just back up a little bit. Why are there so many different ways of moving? Why didn't Mother Nature hit on one solution and stick with it? Because movement is actually a complex antagonism between four competing factors. If you want to get from point A to point B, you can do it faster or slower, how much you displace. Depending on the environment through which you're traveling, you can be more or less robust. One of the nice things about legged locomotion is it allows us to move over flat terrain and also very rugged terrain. Our mode of locomotion is robust to flat and rugged surfaces. You may use more or less energy, and you may fall over, depending on your strategy, as you move. All of these four are usually antagonistic in the sense of if you try and move faster, for example, you're going to take a hit in terms of one of the other three components of movement. If you move faster, which of these three do you usually take a hit on? Energy, when you're an adult and you already know how to walk. When you're a child and you're learning to walk and you try and move faster, you're usually taking a hit in terms of stability, right? So everything we're going to discuss in terms of locomotion is striking a different balance between these things. Compared to other animals, compared to other mammals, we're pretty slow moving. In our case, our species, displacement was not what was optimized. What is the thing that we do best in terms of this antagonism compared to most other mammals? Energy efficiency, right? You can eat half a Big Mac, and if you're in good enough shape, you can walk for 10, 15, 20 miles based on the caloric content of half a Big Mac, which is considerable. But in terms of robotics, it's amazing. No robot gets even close to the energy efficiency of human bipedal walking. I think we'll leave things there. You have a quiz due tonight. Graduate students, please arrange to see me sometime this week or next Monday. Sam will be here to tell you about soft robots on Thursday, and I will see you all next Tuesday. Thank you.